Hello students, my name is Shayan Mitra. I am the faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management. Today I am going to take the class of electromagnetic wave, code number ECE501. So let's start with the class. Today's topic will be vector algebra. With this lecture and with the upcoming lectures, we are going to construct the Maxwell equation through the Poynting theory, and the Maxwell equations are the equation through which all the electromagnetic waves are best described. So today's topic is vector algebra. Let's start with today's lecture. Introduction. Vector analysis is a mathematical tool with which electromagnetic concepts are most conveniently expressed and best comprehended. A quantity can either be a scalar or a vector. A scalar is a quantity that has only magnitude, that we have already known from our earlier classes. And scalar quantities such as time, mass, distance, temperature, entropy, electric potential, and populations are scalars magnitude. It means the scalar magnitude is basically any kind of scalar. Scalar concept of scalar is it has only magnitude but no direction. So let's go to the next slide. Vector is a quantity that has both magnitude and direction. Any physical quantity which possesses a direction and a magnitude, both, then it could be called a vector. A vector quantities include velocity, force, displacement, and electric field intensity. A field is a function that specifies a particular quantity everywhere in a region. First of all, we have to understand what is field is. Anyhow, we have to say the electric field. What is electric field really means? Electric field or magnetic field, any kind of field, that it really means is a function that specifies a particular quantity, and that particular quantity will be electricity or magnetic. Is magnetic field, a field that has been created by a magnetic exposure. A magnetic field specify the amount of magnetic power, magnetic energy present in a specific region. And also, if we are talking about electric field, an electric field specifies a particular quantity, and what that particular quantity is, that particular quantity will be electricity. And a specified region where the electricity or the electric energy exists, that particular or specific region will be called an electric field. Now let's talk about the scalar fields and the vector fields. Now the examples of a scalar fields are temperature distribution in a building, sound intensity in a theater, and different kind of many are there. And if you're talking about vector fields, such as the gravitational force on a body in a space and the velocity of raindrops in the atmosphere, are examples of vector fields. In these vector fields, and if I'm talking about a vector field, it means that field which consists the specific physical quantity. That physical quantity possesses the nature of both magnitude and direction. It means that the specific physical quantity possesses direction and as well as magnitude. Let's go to the next slide. Now we're going to start with the definition of unit vector and the significance or importance of unit vector. Now you can already see from this slide that we have already said that suppose there is a vector capital A, it denoted by a capital A, which has both magnitude and direction. The magnitude of A is scalar, as we have already known. If you are talking about only magnitude, it only has a value, a specific measurement, but it doesn't have any direction. So we can say the magnitude of that particular vector A will be a scalar, and it has been written as mod A, only A or mod A. If we are talking about a vector quantity specified by A, and if we are talking about mod A, then that mod A specifies the amount of or the magnitude of that vector, only the magnitude of that vector. Now unit vector A suffix A along A is defined as a vector whose magnitude is unity and its direction is along A. It means if I am talking about a unit vector which has been described as A suffix A, is nothing but a vector A, a vector which is along the direction of vector capital A, but with not the value of that. Okay, it means a unit vector A suffix A will always be with the value of that unit vector will be always 1. That's why it's been called as unit vector. And that unit vector has been described with this equation, where a unit vector A suffix A is equal to capital A by mod A, and this mod A specified the amount of the magnitude of that vector A. This vector A, the magnitude of vector A has been specified by mod A. Now if we divide this mod A, or sorry, if we divide this vector, that this vector with which possess the magnitude and the direction both. Now I am going to divide this vector by this vector which only not only vector, scalar value mod A, which only possesses the magnitude of vector A. Now if we divide this vector A by mod A, we will get this value. Which is it? Now this unit vector only possesses the direction of this capital A vector and the direction. It means we only just suppose there is a value 10. Now if I divide that 10 with 10, what we will get? We will get 1. Now if 10 has a direction over its heads, now that is not going to be divided. Now if we divide the 10 direction with a 10 with in upper hand has got a direction by only the magnitude value, what we will get? We will get 1 with a direction, and this unit vector is nothing but that. It's a unit vector is a vector of the same of this vector. If I am talking about A suffix A, so this, in the suffix A, we got a vector this, we got this vector. The direction of this unit vector is very much same to this vector, but the value will be 1. Now there is a basic we have different significance, because we are going to use this unit vector to express different kind of vectors. Now let's go to get into the next section. What is that? Now this mod A is equal to 1. We know that if we taking the mod of A suffix A, what we will get? We will get this only the value of 1. Then we already know, because unit vector has always always have a value of 1, but it will have the direction of that specific vector with whom which we have divided. Okay, this vector has been divided by the value of the same vector, then we will get this vector which has the direction, and so of this vector, the same vector has the same direction, but the value of A suffix A will be 1, but the direction of A suffix A is equal to the same with this vector A. Now we can see from this equation we can jump to this equation, that this vector A can be written as mod A into A suffix A. Now A suffix A will be will provide the direction of that vector, and A will provide the value of this vector. Now this vector can be defined as this. A suffix A will describe the direction, and mod A, or we can write this in this way. Okay, so this is the it shows the direction and it shows the value. It means this vector A has two components. One has been physically described as the value of the magnitude of that vector, and this A suffix A, which is a unit vector, but it possesses the direction of this vector. It means this a vector can be written as a component, is a multiplication of two units. One possesses the magnitude, one possesses the direction. Now let's go to the next point. Now from this equation, what we will get? We will get which completely specifies. Now it has this line describe that what I have described earlier, that which completely specifies A in terms of magnitude A and its direction A suffix. We just have to imagine that how it has been. This vector A can be, it's a component of these two characteristics, which if we multiply both of them, we will get this. That's the next point. Now a vector A in a Cartesian or rectangular coordinates may be represented as this: A suffix x, A suffix y, A suffix z, or a suffix ax plus a suffix y, a suffix y, small a suffix y, plus capital A suffix z, small a suffix z. What it means? It means a Cartesian vector will we have the coordinates of a Cartesian coordinates. The coordinates of Cartesian vector is what? Is x, y, and z. And if we decompose or we deconstruct a vector A through the coordinates, what will we get? We will get three different categories. A vector A can be described with these three. A vector A, if we put a vector in a Cartesian coordinate, then what will we get? We will get this. A vector can be written as this. This is the value of vector A along the x-axis. This is the value of A along the y-axis, and this is the value of Z. This is the value of A across or along the z-axis. X, y, z in each and every axis. The vector A has three different components. This is along the x-axis, this is along the y-axis, and this is along the z-axis. So a vector A can be written as this, a plus plus plus, it's a position, and this is the total value with direction. So let's go to the next slide. Yes. So this is the pictorial depiction of that. Look, this if you're talking about a unit vector will also have a value along the ax. In the x-axis, along the x-axis, the value of a vector is a suffix x. Along the z-axis, along the y-axis, it will be ay. Along the z-axis, it will be a suffix z. And if I am talking about this vector A, now this is the vector A. Now it has three different components. How? This is along the y-axis. This is the value. This is ax along the x-axis. This is a suffix x into small a suffix x. A small a suffix x describes the unit vector, and capital A suffix x describes the magnitude. So in this way we will get the value across the z-axis. We will get along the y-axis, along the z-axis we will get this value. Along the y-axis we will get this value. Basically any vector can be described or can be deconstructed. If we take a vector can be described along the three different axes in Cartesian coordinate. Okay, so let's go to this point. Now where a suffix x, a suffix y, and a suffix z are called the components of A in the x, y, z direction respectively. That's what I've already said. Now a suffix x, small a suffix x, small a suffix y, and small a suffix z are unit vectors in the x, y, z directions respectively. For example, A is a dimensionless vector of magnitude 1 in the direction of the increase of the x-axis. The unit vectors of vectors a suffix x, a suffix y, a suffix z are illustrated in figure 1.1a, and this is the 1.1a figure. Now, and the components of A along the coordinate axis are shown in figure 1.1, just that what I have described. And the magnitude of vector A is given by this. Now this is a very important factor, that now if we have to calculate the value or the magnitude of vector A, we have to calculate along the with this equation. We have to calculate this with this equation, specifically this equation. Now if I have to calculate the value of A, we will have to take a root of a suffix x square plus a suffix y square plus a suffix z square. It is coming from the parallelogram and triangle. From the parallelogram rule we can take out the magnitude of vector A. And now if we merge all these three vectors which are along the x, y, z axis, we will get the total value of vector A. And as along this, we can also, as from the previous slide what you have seen, we can create this, or we can extract the value of unit vector. Now from this equation what you can see, that this is the real vector that has been described. This is the real vector, this is the vector, this is the total vector. With this vector, a vector A has been described with this x, y, z axis. This equation or this value, it is basically, it possesses both magnitude and direction. Now in this equation what we have, this is the total vector, the value it possesses the both magnitude and direction. Now if we divide this with this value which only possesses the magnitude, then what we will get? We will get the unit vector of this vector A, and this is the whole concept of unit vector. Let's go to the next. Now these are, we have already know all these things as vector addition and subtraction. How it will work, let's discuss it. Two vectors are A and B can be added together to give another vector C, that we have already seen that C is equal to A plus B. Thus if A expressed in this way and B expressed in this way, where this value is along the x-axis, this value is along the y-axis, this value along the z-axis, and same for this. Now what we will get? If we have to add both of them to get this, what we will do? We will just add the components along the x-axis. The component of A along the x-axis is A suffix x, and component of B along the x-axis is Bx or B suffix x. So what we will do? We will add both of them, A suffix x plus B suffix x into A suffix x, and this has been written as Ax. Basically it is A suffix x. This is the unit vector, and the same thing will be repeated. This is for it will be along the y-axis. The components along the y-axis will be summed up, and this is the value of along the z-axis which has been summed up to get this total value. And this is the unit vector along the z-axis, this is the unit vector along the y-axis, this is the unit vector along the x-axis. Now the same operation can be performed for the vector subtraction. The vector subtraction is similarly carried out as D, where A minus B, and the same thing will be the same way of operation can be performed on this thing. What we will do? We will subtract the components. Yes, we will subtract the components along the x-axis. The same thing. This is the value of x-axis. This is the component along the x-axis for vector A, and this is the component for B. This is the component for B along the x-axis. So what we will do? We will subtract along the values those are along the x-axis. Subtract the values along the y-axis. Subtract the values along the z-axis. Now vector addition and subtraction are obtained by either the parallelogram rule or the head to tail rule. Now we will describe that in the next slide. Now this is the parallelogram rule. Now this is how this parallelogram rule works. That this is the value, this is the C, which is a summation of A and B. Now vector A and vector B, if we add them, the addition, the value of the A plus B can be expressed along this axis C, and the direction of A plus B will be also in this way. That's why this C describes the addition of A plus B and has been expressed in this way. That's why it's called parallelogram, which it creates a parallelogram. It creates a parallelogram, and for same can be considered for triangle. This is called triangle rule. This vector A and this vector B, if we add them, we get this vector along this. That's why it's called head to tail. This is the vector addition, and same thing, the same rule can be applicable for vector subtraction also. In the vector subtraction, what we will have? We have A, B, and this is the D. It means A, this is B, and along this direction, and this is the D. Basically A, if we subtract the value vector B from vector A, we get a new vector which will be along the axis D. This is the direction of that A minus B vector, and the magnitude also will be expressed in this way. Same thing will be applicable. Same thing will be applicable to this. Now, graphically, vector addition and subtraction are obtained by either the parallelogram rule or the head to tail rule, as because this is a head to tail, that's why it's portrayed in figure 1.2 and 1.3. This is the figure 1.2 and this is the figure 1.3. Now, three basic rules of algebra obeyed by any given vectors A, B, C, and this is important, are summarized as follows. First of all, This is a commutative law. This is a plus b is equal to b plus. It means we can write a plus b in a this way, b plus. Associative rules, what is that? It is a plus in the bracket b plus c. We can also write a plus b in a bracket plus c. Both a plus b is equal to b plus a are similar. A plus b in bracket b plus c is equal to bracket a plus b plus c are similar. And distributive, in case of distributive law, if we multiply this a plus b with a magnitude, we will get this. If suppose this is a magnitude k or l, anything a plus b, if we multiply this with a plus b, we will get ka plus kb. This is the distributive law, this is associative law, and this is commutative law. Okay, so let's go to the next slide. Okay, now there is a important factor that you should discuss here, that this is the last one, is that position and distance vector. With distance vectors, how it works, let's see this. A point P in Cartesian coordinates may be represented by x, y, z, because any point will be described with there are three different axes. So any arbitrary point can be described with three different coordinate x, y, z. We will express the position of a point, any arbitrary point, with three different points, with three different values of that point. So let's extract from this. The position vector rp, or radius vector, the position vector can also be called as radius vector, of point P is as the direct distance from the origin to P. It means basically rp is the distance of the point P from the origin. Now if we have to calculate the distance of that point P from origin, what we will do? We will get this. So this is the position of a point, and the position vector is rp of the point. This is the direct distance from the origin to P. This is the position vector. Now if you are talking about the distance vector, the distance vector is a displacement from one point to another. So there is a basic difference between these two. One is a position vector. Position vector is the direct distance of point P from the origin to P. Okay, if you have to take a distance, the position vector of rp is the point P is as the direct distance from the origin to P. This is position vector, and the distance vector is a displacement from one point to another. Both are absolutely different. Position vector is the distance of a point from origin, and the distance vector is the displacement from one point to another. So if you have to calculate a displacement from one point to another, what we will do? If 2 points P and Q are given by xp, x suffix p, y suffix p, and z suffix p, and x suffix q, y suffix q, and z suffix q, the distance vector or separation vector is the displacement from P to Q, as shown in figure 1.5. That is, r suffix pq is rq minus rp. This is basically this, from this position this point displaced from P to Q, or from P to Q. So the basic distance between both of them can be expressed with their position, xq minus xp along the x axis. This is for along the y axis, and this is for along the z axis. If we subtract from along the x axis, along the y axis, along the z axis, we will get the distance vector r suffix pq. This is the example of distance vector r suffix pq. Let's go to the next slide. And now the very important part is the difference between a point P and a vector A. That's a very important part. Let's have a very close look. The difference between a point P and a vector A should be noted. Though both P and A may be represented in the same manner as the difference between a point P and a vector A should be noted. Though both P and A may be represented in the same manner as x, y, z and a suffix x, comma a suffix y, comma a suffix z respectively, the point P is not a vector. Only its position vector rp, position vector rp is a vector. The vector A may depend on point P. However, for example, A 2xy a suffix x plus y square a suffix y minus a x z square a suffix z, and P, this is 2 minus 1 comma 4, then A at P would be this. This P, this is the position. Okay, this is the point which has been described with this position. and the a at p, a is a vector which can be described at point p, and this would be described with this minus 4x plus a suffix y minus 32 a suffix z. Now x y, y and x z at the point. Now p is 2 comma minus 1 comma 4. Now we will put this 2 in place of x, we will put this minus 1 in place of y, we will put this 4 in place of z, and if we consider these values, we will get the vector a at point p. This is the basic difference. Now this vector has been described with this, and this is the position of point p. Now vector a, the value of vector a at point p would be this. A vector field is said to be constant or uniform if it does not depend on space variables. A vector field is said to be constant or uniform if it does not depend on space variables x, y, z. So if you don't have a x, y, z, therefore, suppose this is the example of that. Suppose vector b has been described like this, 3, 2, 10. So all these are constant value. So at any point, at any arbitrary point, the value of vector will be same. But this vector, it has an arbitrary point x, y, y, z. So with each and every point, the value of the vector will be changed. So that's why it's not a uniform. But because b is a same everywhere, whereas a varies from point to point, because vector b has been described with this, where there is no arbitrary point has been included. So if there is no point has been included, so the vector b will be constant in every point or uniform in every point. But in case of a, it has not been applied. So after that, we will go to the next slide. This is a different matter. This is a useful symbol and their value I have put all together for so useful for the purpose of the exam. These values will be these values are important. This had been included for further studies. It has been stored. So up to this, we'll close this class for the lecture 3.